Welcome to Learning Management System e-learning. In this video, I have provided the complete proof of an important theorem, Cayley's theorem in permutation groups. It is very important theorem for semester 3 degree second year students. Statement of Cayley's theorem. Every finite group G is isomorphic to a permutation group G'. Finite group G is isomorphic to G'. G is isomorphic to G' means first we define a relation from G to G' which satisfies three conditions: 1, 1, onto, and homomorphism. That is the definition of isomorphism. 1, 1, onto, and homomorphism. So permutation group. Permutation group, first we define a permutation. Permutation means a bisective mapping is called a permutation. Bisective means 1, 1, and onto. Proof. Let G be a finite group and A belongs to G. Define a mapping FA G to G as FA of X is equal to AX. Very important relation. FA of X is equal to AX for all X belongs to G. It is denoted by equation 1. First we show that FA is a permutation. Permutation means 1, 1, and onto, bisective mapping. First one, FA is a 1, 1. Suppose FA of X is equal to FA of Y. General definition of 1, 1, F of A is equal to F of B, that gives A is equal to B. Here, FA of X is equal to FA of Y, using 1, FA of X is AX, FB of X is BX. This is AX is equal to BX. Since A and X, A and Y are elements in G, cancellation laws are held in groups. By using left cancellation law, A cancel, that gives X is equal to Y. So FA of X is equal to FA of Y gives X is equal to Y, which means FA is 1, 1 mapping. Second one, FA is onto. By definition of onto, every element in the codomain having pre-image element in the domain. Here, G and G' are G is domain, G is also codomain. So here, G, every element in the codomain. Let Y belongs to G, codomain. Then there exists an element X is equal to A inverse Y. Suppose FA of X is equal to AX. So FA of X is equal to AX. By using 1, FA of X is AX is equal to Y. So both sides multiply with A inverse. And by inverse property, A inverse equal to A inverse A is equal to E. By identity property, AE is equal to EA is equal to A. That is, X is equal to A inverse Y. Domain such that FA of X is equal to FA of X. X is A inverse Y. FA of A inverse Y. FA of A inverse Y, that is equal to, by using 1, FA of X is equal to AX, that is A into A inverse Y. Associative law, A inverse, changing the bracket. So A inverse into Y, that is equal to A inverse is E, that is E into Y is equal to Y. So by identity, E into Y is Y into E is equal to Y. So FA of X is equal to Y. That means every element in the codomain having pre-image element in the domain. That is FA is onto map. Clearly, FA is 1, 1 and onto. 1, 1 and onto means FA is a bisective mapping. Bisective mapping means it is a permutation. FA is a permutation. Let G' is equal to FA such that A belongs to G. FA is a permutation with the set of all permutations of G. First we prove that G' is a group. By definition of a group, G' satisfies closure, associative, identity, and inverse. The first one is closure. Take two permutations. FA, FB belongs to G', where AB belongs to G. A and B are elements. FA and FB are permutations in G'. Now, FA circle FB of X is equal to FA circle FBX. So, by the composition of mappings, F circle G of X is equal to F of G of X. This is the composition of mappings. First, we perform on G. FA circle FB of X is equal to, by using 1, FA of X is equal to AX. FB of X is equal to BX. This is Bx. Fa of Bx is equal to A into Bx. So Fa of x is equal to Ax. Replace x by Bx. So A into Bx. By changing associative, A into Bx equal to AB into x. This is AB, FAB of x using 1. Fa of x is Ax. FAB of x equal to AB of x belongs to G dash. This shows the composition of mapping circle is a binary operation in G dash. Here, FA circle FB equal to FAB. Similarly, FB circle FC equal to FBC. So Fx circle Fy equal to Fxy. Remember, this is very, very important. Fa circle Fb equal to FA. Second one, associative. Take three permutations. Fa, Fb, Fc belongs to G dash, where ABC belongs to G. Now Fa circle Fb circle Fc equal to Fab. First we perform on Fa circle Fb using 2. Fa circle Fb is Fab circle C. Now applying Fab circle Fc. So Fab to C. Fab. By using associative, change the bracket. Fa to B. ABC. ABC is A into BC. This is Fa circle. Fa circle FBC. Fa circle. Again, Fa circle FBC is FB circle FC. So LHS. Fa circle FB circle FC is equal to Fa circle FB circle FC. This is A into BC equal to AB into C. This is the operation circle is associative in G dash. Third one, identity. Take two permutations. Fa, Fb belongs to G dash, where AB belongs to G. Let E be the identity element in G, then we have A is equal to EA is equal to A, identity property. Now Fa circle Fe is equal to Fa circle Fe using 2, Fa circle Fb is equal to Fab. So FAE, A is equal to A, this is Fa. Again, Fa circle Fa is equal to FEA, EA equal to A, this is F. Therefore, Fa circle Fe is equal to Fe circle Fa is equal to Fa. This means Fe is the identity permutation in G dash. Here, AE is equal to EA is equal to A is the identity. The fourth one is inverse. Take two permutation Fa, Fb belongs to G dash, where AB belongs to G. Since AB belongs to G, A inverse, B inverse also belongs to G. Since G is a group, by inverse property, every element having multiplicative inverse. And A inverse is equal to A inverse A equal to E. This is the inverse property. Now, Fa circle Fa inverse equal to, using 2, Fa circle Fa inverse is Fa inverse. Fa inverse is Fe. Again, Fa inverse circle Fa is equal to Fa inverse A using 2. Fa inverse A inverse A is E. This is Fe. So Fa circle Fa inverse equal to Fe is equal to Fa inverse circle Fa. This means Fa inverse is the inverse element of Fe. So every element having inverse in G dash. Clearly, G dash circle is a group. G dash is a group with respect to composition of mappings. This group is called the regular permutation group. G dash is a permutation group. Now we prove that G is isomorphic to G dash. G is a finite group already given. G is a finite group. G dash is a permutation group. We prove that G is isomorphic to G dash. Isomorphic. First we define a mapping pi G to G dash as pi of A is equal to Fa. Pi of A equal to Fa. G dash is the set of all permutations. Fa is a permutation. A is a ABC are elements in G. Pi of A is equal to Fa. Equation 3. Now we prove that pi is an isomorphism. Pi is an isomorphism. Isomorphism means pi is 1-1 onto and homomorphism. The first one is pi is 1-1. Let AB belongs to G and pi of A is equal to pi of B. 1-1 definition. Pi of A is equal to pi of B. Means pi of A is using 3. Pi of A is equal to FA. Pi of A. This is pi of B is equal to FB. This is equal to FA is equal to FB. This means FA of X is equal to FB of X for all X belongs to G. FA of X means AX. Using 1, FA of X is equal to AX. AX is equal to FB of X is BX. So A and B are elements. By using right cancellation law, XX cancel. Here A is equal to B. So pi of A is equal to pi of B gives A is equal to B. Therefore, pi is 1-1 mapping. The second one, pi is onto mapping. Onto mapping means every element in the codomain having pre-image element in the domain. So FA is domain. Codomain is G dash. G dash contains permutations FA. FA belongs to G dash, where A belongs to G. Then pi of A is equal to FA. With the definition of equation 3, pi of A is equal to FA. We defined a mapping, which gives pi is an onto mapping. So every element in the codomain having pre-image element in the domain A, pi of A is equal to FA is the onto mapping. Third one is homomorphism. Let A comma B belongs to G. Now pi of AB. So here the binary operation in the domain is dot. Pi of AB. Pi of AB means pi of A dot B. A dot B. Pi of A dot B. Pi of is using 3. Pi of A is equal to FA. So pi of AB equal to FAB. FAB means FA circle FB. Using 2. FA circle FB. FA means pi of A circle pi of B. So here operation in LHS is dot, general definition. In operation, binary operation in codomain, G dash is circle. So pi of A dot B is equal to pi of A circle pi of B. Means pi is homomorphism from G to G dash. Clearly, pi is 1-1 onto and homomorphism from G to G dash gives pi is an isomorphism, which is the definition of isomorphism. Pi is an isomorphism from G to G dash. This concludes that G and G dash are isomorphic group. So pi is a homomorphism, pi is an isomorphism from G to G dash. Then we say that G and G dash are isomorphic groups. That is,